This tutorial helps illustrate how to approach any type of conservation of energy problem. In this problem here, we have a 77 kilogram diver drops from a board 10 meters above the water surface. We need to find the diver's speed just before striking the water. Now we're going to start by drawing two pictures, an initial and final. So our initial and final conditions. So in the beginning here, we have a diver that is 10 meters off the surface. We have that his mass is 77 kilograms. We have that the height is 10 meters. We'll label that the initial height. And the initial speed, well, the diver is not moving in the beginning. So if we call this height to 10 meters, that's defining the zero level at the water surface. So I'll label that down here, that the water surface is the zero level. In our final conditions, the diver is now moving, still has a mass of 77 kilograms. Our height final now is 0 meters. We're at the water surface, and we're supposed to find the final speed. Well, we say that energy is conserved, and we're neglecting any kind of air resistance or friction, and so our equation says that the total energy in the beginning, and we have three forms right now. We have elastic potential energy, we have gravitational potential energy, and we have kinetic energy. Those three forms in the beginning are equal to those same three forms at the end. The numbers just transfer from one type to another. So if the potential energy goes down by 10, that would mean the kinetic energy would go up by 10, but the total would stay the same. And so now for each of these three here, we want to think about whether energy is present. Well, we have our three forms. How do we know if we have these types of energy? Well, we have elastic if anything is being stretched or compressed. And our equation is 1/2 kx squared, where k is the spring constant, which is the strength of the spring, and x is the distance stretched or compressed. Gravitational potential energy we have if we are above or below 0. And our equation is mgh. M is the mass, g is the gravitational field, and h is the height above or below 0. We have kinetic energy if we are moving. And our equation is 1/2 mv squared, m being the mass and v being the speed. So we go back here, and we have that nothing is being stretched or compressed. I'm going to put zeros in for both of those. And we're left with mghi plus 1/2 mvi squared is equal to mghf plus 1/2 mvf squared. So again, if you have a spring constant, if you have something being stretched or compressed, you would include on both sides 1/2 kx squared. But because we don't have either of that in this situation, I'll just leave those out. Now we can put those values in, and let me just say that we could, if we wanted to, cancel out these masses. As long as there's a mass in every term. A term is a group or collection of values multiplied or divided together. So terms are broken up by pluses and minuses. So we have one term here, one term here, one term here, and another term here. If they all have mass, then we can cancel those out. But they must, every single one of them must have mass. So I'm just going to write the numbers in anyway, though. Mass of 77 kilograms. Gravitational field is 9.81 newtons per kilogram. Height is 10 meters. Now, 1/2 the mass times 0 squared is 0. So I'm just going to write 0, save myself a little bit of room. Same thing on this term here, this gravitational potential energy at the end, since my height at the end is 0, 77 times 9.81 times 0 is 0. So I just need to save myself some room because I don't have as much space. Then 1/2 the mass, which is 77 kilograms, times Vf squared. That's what we're trying to solve, Vf. So now we can solve for this. We multiply and divide everything over, and we get our final speed as 14.0 meters per second.